Hi, in this video we'll see what graph traversals are, how many types of traversals are there and how do we do it and what are its applications and how does it help in our real life. So we have two types of graph traversals. One is breadth first traversal and the other one is called depth first traversal. And we should know for the first line that the time complexity of both these traversals are big O of V plus E. Now, what is all this? How do we find out the time complexity for these algorithms? We'll just see. So, we begin with breadth first traversal. Let us consider this graph and see how do we do it in this traversal. Breadth first traversal is also called level order traversal. Now, these names itself suggest why are they called so. Level order traversal means you start from one level, then you go to another level and cover all the vertices of that level, then you go to the next and then you go to the next level. You go level wise. Breadth also means you go breadth wise. You don't go the way we go in depth first. You don't go deep down. You go breadth wise. So let us see how does this work. What do we need in this? So first of all, there's a data structure that we need for breadth first traversal, and that data structure is Q. We need a queue and also an array. Now the array should be of size equal to the number of vertices in the graph that we have. Now why do we need of that size? For example, let us see, we have from A to H. Let us make an array from A to H. A, B, C, D. Now what do we do? That we take this array and we initialize it with the value 0. We initialize all the vertices with the value 0. Now this is also called as your visited array. What do we maintain in this is that if you have not visited the vertex so far, the value is 0. If you have visited the vertex, the value will become 1. And we do this so that we do not repeat or we do not visit a vertex again. So we begin with the algorithm here. You have the breadth first traversal function, BFT, and you give it a vertex as a parameter which we consider as the source vertex. You can take any of these vertices as the source. So supposing if you take B, this will be the first level, this will be the second, this will be the third level. Basically the level means the distance of the vertex from the source. All those vertices which are at the level or at distance 1 will be on the level 1, and which are at a distance 2, the shortest distance 2, they will be on the level 2. So we see that we have our source vertex. For in this case, let us take A as the source vertex. So as you begin, you have visited A, so you make the visited of V, that is visited of A, equal to 1. So let us make it equal to 1. Now you add A to a Q. You add A to a Q. We have used this data structure Q. Now why have we used this? You'll know soon. So we add A to the Q. Now while the Q is not empty, the Q isn't empty, it has A. X is equal to delete Q. The delete Q function will give you the first vertex or the first element that it visits in the Q. So delete Q here will return A. So now X holds A. Now you'll do print of X. Okay, so since we are traversing, we must know in what order we are traversing. So we print A. Now we enter a loop. Now for all the vertices that are adjacent to X, we are taking W as a variable for all the vertices adjacent to X. X is A. Now the adjacents of A are those which are at a distance of 1 from A, or which are at a level 1. If we consider level of A as 0, then all those which are at level 1 are the adjacents of A. So while or for all the adjacents of A, we consider B over here. Now if B is not visited, make the visited of B is equal to 1 and add B to the Q. you have already deleted this. This is out. Let us maintain another Q over here. This A is out, so you put B over here now. So this round is over. Now another adjacent of X is C. So if C is not visited, make it 1. Add it to the Q. If D is not visited, make it 1 and add it to the Q. Similarly, if E is not visited, make it 1 and add it to the Q. Now we see we do not have any other vertex which is at a distance of 1 from A. So for all this, we come out of this for loop and we go into another round of the while loop. Now we have to go on while the Q is not empty. The Q is not empty. So X is equal to delete Q. Now Q follows the property first in, first out. So B came in first, so B should go out. So delete Q will return B. And X now has B. So we print X. So we'll print B. And then we'll come here and we'll visit all the adjacents of B. So we check here. One adjacent of B, that is A. Now, is A not visited? No, we see A has the value 1. It is already visited. So we won't go in here. We check for another adjacent of B. We find it F. Now, is F not visited? So we see yes, it is not visited. So we make the visited of F1 and add it to the Q. And then we go on ahead and find out any other adjacents of B. There is no adjacent of B. So we come out of the for loop and we go into another round. Now while Q is not empty, the Q isn't empty, B is out. Now X is equal to delete Q. C, so you delete C. X now has C and you print C. Now for all the adjacents of C, you check here. A is visited. F is also visited. Do we have any other adjacent of C? No. So we come out of the for loop. Now the Q is not empty yet, so we delete again the first element and we print it. Now for all the adjacents of D, A is visited, G is not visited, so we make it 1 and add G to the Q. Do we have any other adjacent? No. So we go into the next round. While Q is not empty, delete. Okay, here we had gotten A and now we have, we had got D and now we have E. Now print E. Now we check the adjacents of E. A, it is visited. G, it is visited as well. So we do what? We cannot do anything. So we move on to the next round of while loop and we check, is the Q empty? No. We still have something. We now have F, so we print F. Now we check the adjacents of F. B visited, H not visited. Make it visited and add it to the Q. Now after we add it to the Q, we also had to print, we have printed F, I'm so sorry. So we have added it to the Q. Now we don't have any other adjacent of F, so we exit the for loop and we check, is the Q empty? No. So we go in and we take X is equal to G. We delete it, print it here. Now for all the adjacents of G, E visited, H visited, so we will not go in here. And D, we also have D, that is also visited. So we get out of the for loop and we go on to the next element. Is the Q empty? No, the Q is not empty. So X now holds H and we print H. Now we check, actually we don't need to check also because we already have the visited array holding 1 and only ones. There is no 0. So we have our breadth first traversal sequence over here. Now let us see what has happened. The first level we took as A. We have printed A. Next level we took as this. So we have in this level B, C, D, E. We have B, C, D, E printed. In this level we took F and G. We have F, G printed and then we have H printed. So you see we go level wise and print it. We'll also see the time complexity. Now if you see, this Q holds how many elements? Only those many elements that are equal to the number of vertices. So this while loop will actually run V times, and for all the adjacents of every vertex, if you sum this up for every vertex, what will happen? For B, supposing you take, once A had its adjacent B, so this edge was counted. But when you reached B, B also had its adjacent A, so this edge was counted once again. So you see that when we apply this to all the vertices, actually in the for loop we'll be traveling 2e times. This entire loop will go on a total number of 2e times. So how we have learned that a loop within a loop, actually supposing if this runs V times and this is big O of E times, then it should actually, because it is a loop within a loop, it should give big O of V E times. But we see that we have the time complexity as big O of V plus E. How does this happen? So let us just check what is happening. You have this loop big O of V into, you have some operation going on which takes a constant amount of time, so you add 1 over here, big O of 1, plus you have this loop. Now let us consider the individual time, forget this. So for 1 it must have run certain number of times, so actually it is running for Vi into, we have Vi into the adjacent of that vertex. If we try to generalize it in a better way, we'll see that we have big O of V, big O of 1. Let's just add these two together. And if we just try to open it up, we'll see we have how many adjacents. Let's try to write 4 plus 2 plus something. If you sum this up, let's just open up the bracket. Big O of V, when we multiply this together, and big O of V into 4 plus V 2 plus something. So actually a sum of all this gives you big O of 2E, and you have big O of V, which gives you further as big O of V plus E. So this is from where you get the time complexity as big O of V plus E. Also, we should analyze the space complexity. So space complexity in any algorithm is generalized as input plus the extras that we take. Now we have been given a graph as an input, and a graph can be given as an input to the computer only in 2 formats, either as an adjacency list or as an adjacency matrix. Supposing that we have got the graph as an adjacency list, then the space that it will take will be V plus E, where V is the number of vertices and E is the edges. And we have taken array as an extra and Q as an extra. Array has the size of V, so we take the space as V, and Q also contains only the vertices, so it also has a size V. So in all, if we sum this up, we get space complexity also as big O of V plus E. We'll see the applications of BFT in the next video. Do watch that as well. Thank you.